ก่อนนะครับเดี๋ยวนี้โชคดีเรคคอร์ดนะครับกลับไปฟังซ้ำได้นะสมัยก่อนนี่ฟังแล้วฟังลับหายไปเลยเดี๋ยวนี้ก็สามารถที่จะฟังซ้ำได้นะครับ Okay, so today everybody hear me, right? Everyone, we have about 6 or 7 students right now. Hello, everybody hear me?
ครับ
Okay, so today we are going to talk about the combustions in the internal combustion engines. Right? We have two types of engines, right? The SI engines and the CI engines. So we will talk both combustions, right, in these two engines. Okay, so the first one we're gonna start with the combustions in the SI engines. Okay, right. So generally, right, the combustion in the spark ignition engines, right, usually or normally begin at the spark plug here, right. So at the spark plugs, right, around the spark plug here, right, we have the molecule, right, the molecule that in and around the spark discharge of this molecule are activated due to the spark discharge, right, and it receives the energy up to the level where the reaction is self-sustained. So what does it mean here by self-sustained? It means if you look at the picture of the combustions, for every single cycle, the spark will do only once, right? Will discharge only once, right? And the rest of the combustion that happen, right? It have to go on by itself, no help from the spark plug for every one single cycle, right? Until the next cycle come in, the spark start to discharge again, okay? And after it discharge, it stop. Combustion happen, right? And that combustion have to help itself, right, to keep going on until finish. Okay, so combustion that happen in the SI engines, right, may be one or more of the following type of combustions. Right? First is called normal combustions. The second one is called abnormal combustions, and the third one is uncontrolled combustion. We will talk all of these combustions. Right? Okay, start with the first one that we call normal combustion. This is the combustion that we would like it to happen in our engine. Right? For the normal combustions, there are 3 stages that may be distinguished during the normal combustions. The first state we call is the ignition lag state. You may hear ignition delay or you may hear time delay. Right? They are the same thing. But in here we call the ignition lag state. Right? What is the time where this ignition lag state happen? Right? It happens when we start to ignite. Right? Okay. And we start counting the time, right? When it starts to ignite the fuels. Right? Until what? Until we can see a noticeable rise in pressure due to combustion. Right? So as long as we don't see the pressure rising rapidly, right, in the engine, in the combustion chamber, right, that means it's still, that combustion is still in the ignition lag state here. Right? So in overall, the ignition lag state, right, is the time interval between the instant of the spark and the instant where there is a noticeable rise in pressure due to combustion. Right? And this always happen before the top dead center. Right? So this is where it happened. Right? This is the period of the time where the ignition lag state happen. Start from A to B. Right? It finished at B because we now see that our pressure in the cylinder, right, start to departing from the pressure due to compression only, which we call is the motoring curve here. Right? This is the pressure due to compression only. Right? And then at B here, we start to see that the pressure in our cylinder start to deviating from the motoring curve here. So the ignition lag state stop right here, right? And the time between A to B, right, is the time interval for this ignition lag state to happen, or equivalent to the distance that the crank angle travel, right? Crank angle travel here. So during the ignition lag state, what happened? Right? What happened during the ignition lag state is that there is a chemical reaction process that happened. And this chemical reaction process do what? It will make this molecule to get heat up. So the temperature of the fuel inside start to increase and go up to self-ignition temperatures. So that means what? In overall, right, during this ignition time lag state or ignition lag state here, the molecule get ignited and then it going to produce a self-propagating nucleus of flame. Right? When we talk about flame, it means combustion start to happen. Right? Without flame, no combustion. Right? So if you see the flame start to happen, that is the start of combustion. Right? So the ignition lag state is the time for the molecule to get heat up until its temperature go up to self-ignition temperatures. And then that means it's now going to produce a self-propagating nucleus of flame here. Okay, so since it depends on the chemical reaction that happen, right? So let's look at the chemical process that happen depend on what? Right? The chemical process that happen depend upon the nature of the mixture compositions, how well that we can mix the air and fuel, and what are the proportions between air and the fuel in our mixtures. Right? Depend on the temperature and compression and pressure. Right? That depend on the compression ratio, how much that we can compress. Okay, depend on the proportion of the exhaust gas. Right? How much that the exhaust gas that leave or left over inside our cylinder. Right? We know that not all the exhaust gas that will go out. Right? Some of the exhaust gas still keep inside the cylinder. So it depends on how much or the amount of the exhaust gas that left over inside the cylinders. Right? It depends on the rate of oxidation or burning. Right? So it depends on how fast that the flame can travel. Right? The flame velocity, how fast is the flame velocity? Okay, so it depends on this, the rate of oxidation or burning, and the last one is depend on the turbulence. Right? How can you make the flow inside to be more and more turbulent here? Okay, so usually the ignition lag state is very, very small, right? And the time interval for this ignition lag state is in between 0.00015 to 0.0002 seconds, right? Or we can talk in terms of milliseconds, right? So to understand this very, very short time here, right? Compare with the crank angle rotation. I show you here that if our ignition lag state, let's say about 0.002 seconds, right? This 0.002 seconds, right, will correspond to the crank angle rotations about 36 degrees on the condition that the engine is running at 3000 RPM. How do we can come up with this? Okay, how do we can come up with this? Right. This is theta, this is the crank rotations, and this is the engine speed, right? The revolution per minute. Right. Each revolution we have 360 degrees of crank angle, right? And since this is RPM per minute, so we divided by 60, and then time with the time that happened, right? Or the time that this crank angle theta, right? This crank have to travel for this theta, right? So you time 3000 times 360 divided by 60 times 0.002, right? And this theta gonna be about 36. Okay. So no matter how big the engine is, what size of your cylinders, right? The crank angle rotation is always the same. This is the characteristic of the SI engine, right? No matter how big your cylinder is, the crank angle for each revolution is always equal to 360. Okay. Okay, so that is the first state here, right? The ignition lag state where no combustion happen, only the fuel get heat up, right? We need time for the fuel air mixture to heat up, right? Until it can generate the flame, and that is when the combustion happen. Okay, so now when the combustion happen, we come into the second state. This second state we call is the flame propagation state, right? So the flame propagation state, it means now you start to see the flame traveling, right, throughout the combustion chambers. Okay, so it is a physical one because you can see it. You can see it, right? But the first one you don't see. You don't see what happened inside, right? You won't see what happened inside until you see the frame. Okay, right? But in the second state is a physical because of this. Right? You can see it when we talk anything about physical. You can see it. Okay, and this state is concerned with the spread of the frame throughout the combustion chamber. Right? That means what you see is you see the flame traveling throughout the combustion chamber. Right? So the starting point of this state is where the ignition lag state stop, right? Which is what? The first measurable rise of the pressure on the indicator diagram. Okay, now you start to hear the word indicator diagram. Before that, we used to say it's the pressure versus volume, or pressure versus crank angle rotations, right? All of these are called the indicator diagram. Indicator diagram, right? So this one is the indicator diagram here. Okay, so that is what? That is the point where the line of combustion, as we mentioned, depart from the compression line and can be seen from the deviation from the motoring curve. Yeah, right. So this is the finish point for the first state and also the starting point for the second state here. Right. So in here, right, just before the piston move up to the top dead centers, you start to see the flame of the combustion. So the combustion start during compression. Compression had not finished yet, right? Because the piston does not move up to the top dead centers, right? And the ignition also happened during compression stroke here. Okay, so from this point on, now you start to see the flame. That means combustion happened, and the flame that travel or propagates, right? It will propagate practically at a constant velocity. At a constant velocity, right? The heat transfer start to happen, but mostly happen on the fuel air mixtures. Mostly it happen on that because the flame just start to travel, right? So the amount of heat transfer at the beginning of this state to the cylinder wall is still low, right? Because only small part of the burning mixture come in contact with the cylinder wall during this period. Okay, most of the heat now just try to go to the air fuel mixtures, right? And the flame just start to happen, right? So it's not wide enough to make contact with the cylinder wall. So only small amount of the heat transfer that go to the cylinder wall, right, at the very beginning of this state here. Okay, right? And since this is where the combustion happen, right? So we have the heat transfer or the heat release. The rate of heat release that happen, right, depend largely on the turbulent intensity, right? How much that we can make turbulence to happen inside, right? And the rate of heat transfer also depend on the reaction rate, right? How fast that the chemical reactions can happen, right? So it depends on these two factors, the rate of heat transfer. First, on how much that we can create the turbulence inside the combustion chambers, and how fast that we can create the chemical reactions, right? And this chemical reaction rate depend on the mixture compositions, okay, or the air fuel ratio here. Yeah. Now, since you see the pressure start to rise, right? Pressure start to rise, right, from point B here, right? So the question is, what is the rate of this pressure rise, right? How fast that we can make this pressure rise to go up very quickly? Because what? Because as we already mentioned, right, in previous lecture, we would like to have this peak pressure here getting closer and closer to the top dead center, right? This is where we want, and theoretically it happen like this, right? But practically it never happened. But we just want to make this peak pressure here at point C getting closer and closer to the top dead center, right? So that means we would like the pressure here, when it start to go up, it have to go up very, very quickly, right? Or highly slope here, right? So that the peak happen near the top dead center, right? So we have to look at how the rate of the pressure rise, right? It depends on what? Okay, the rate of the pressure rise is proportional to the rate of the heat release, right? So it depends on the amount of heat transfer, right? Only. Why? Because during this state here, right, if we can make this peak pressure getting closer and closer to the top dead center, right, it means what? Our combustion process can be happen during the constant volume, right? This is the key point. We want our combustion process, right, to happen in the constant volume here, right? If we can do it at closer and closer to the constant volume, you can be sure that you can get most of the energy out from the fuels. Okay, so that's the reason why the rate of the pressure rise is proportional to the rate of heat release, right? See, if we start our combustion start here, and our peak pressure start right here, right? The difference between this volume is very small. You see the crank angle travel in a very small distance. So our combustion chamber is nearly a constant volume. Okay. Okay. So in overall here, you can see that there is the delay period start from the occurrence of the point A here, the ignition point, right? So this is the delay period here, and this time delay here before combustion start to happen, right, is independent of the engine speed. Okay, the time delay, the amount of the time delay here does not depend on the engine speed. Okay. What does it mean here? What does it mean here? It means that this time delay, no matter what the engine speed is, right, for a certain engine, right, it will be constant. And the key point of the constant is what? Is that if your engine speed increase, and you do or you start the ignition at the same crank angle, no matter what your engine speed is, the peak pressure here will move away or move further away from the top dead center, right? Okay. Because the time delay here, right, does not depend on the engine speed. So if your engine speed increase and you ignite at the same crank angle, right, you can expect that your peak pressure here, right, will tend to move to the right or further away from the top dead center. This will happen, right? So when you increase your engine speed, the starting of the ignition lag state have to happen earlier in the cycles, right, in order to keep the best positions for the peak pressure, and that best position is close to the top dead center, right? So when the engine speed increase, you have to ignite earlier. Otherwise, your peak pressure will move away from the top dead center, and that is something that we do not want to happen. Okay. Okay. The peak pressure here, right, is the point that give us the information that the frame travel is completed. No more frame propagations in here, right? No more frame propagation happen after this, right? So we can see that our frame propagation stop when we know where is the peak pressure here, right? Okay. So even though that the frame travel stop, no more frame propagations, but the heat of the fuel, the whole heat of the fuel had not been yet liberated or delivered, right? Because we still have the after burning effects after that, or the third state of combustion after here. Okay, so the ignition start during compressions, the combustion start during compressions, and keep going on until compression finished, and still going on when the expansion stroke happen, right? Because after TDC here, the expansion stroke happen, right? So if you ride along this curve, right, or you are on the top of the piston, right, you will see that when the piston start move closer to the top dead center, ignition happen, right? You still feel compressions, right? And then when combustion happen, you still feel compressions because the piston still moving up, right? And then when compression start to keep going, right, keep going, right, then you will see that the compression that happened to you or the fuel now release, right, now release. because the piston start to move down, right? But the pressure on you still going up, right? Now this pressure going up because of the combustions, right? Because during this time here, the engine is under expansion stroke. The pressure is supposed to release, but it's not released because combustion happened, right? And it go up until here, the peak pressure here, right? The peak pressure here, where you see no more combustions because no more flame propagations, right? But the heat transfer still happen, right? So you have to separate between combustion and the heat transfer, right? Okay. When we start to have combustion, it doesn't mean we have a lot of heat transfer, as we already mentioned. And when the combustion finishes, it doesn't mean that there is no more heat transfer. There is still heat transfer, right? And that's why we have the third state called the after burning state. The after burning state starting point is usually taken as the instant at which the maximum pressure is reached, which is point C here. So this is the starting point of the third state here, right? The frame velocity decrease. That's why it's no frame propagation. It decreased during this state here, right? The rate of combustion become low because of the low frame velocity and also because of the reduced frame front surface, right? The frame front surface start to reduce, right? No more pressure rise during this state. What you see is pressure start to decrease in the third state of combustions, right? Because expansion stroke already start, right? With the piston moving away from the top dead center, right? So combustion start to reduce or no more combustions, so no more pressure rise in here because the expansion stroke happen also here. Okay, so I show you another indicator diagram. This one is on the PV diagram in which, right, I show you here just because I want to show the all three states of the normal combustions that happen. Okay, right. So at point C here, the ignition start before it go to the top dead center. Yeah, because you see the volume here, it's not reached the top volume here. Okay, and then it keep going on until it's finished here, where the compression end. Right? We know it end because it's already at the top dead center, the minimum volume. Right? And then the second state happen. The pressure still keep increasing until at point D here, where maximum pressure happen here. Right? So the second state finish here, and then the last state start to happen, and it stops somewhere around here. Okay. Okay, so that is the normal combustion, which consists of three states of combustion. The first one is the ignition lag state, right? And flame propagation state here. And the last one is the after burning state here. Okay, so let's look at the effects on the engine parameter or variables that have on the normal combustions. Start first with the effects on the ignition lag state, right? The first state of the normal combustions. The first engine variable is the electrode gap on the spark plug. Where is the gap that we mentioned here? It's shown right here. Right? This is the gap of our spark plug here. Right? The yellow look like yellow or orange here. This is the electrode here. Right? So this is the gap that we mentioned. Now, if this gap happen to be small or too small here, what happened is you might have the quenching of the flame nucleus. Quenching of the flame nucleus, that means you have no flame happen because the gap is just too small, right? So it spark but no combustion because there is no flame nucleus happen, okay? And the length of the fuel air ratio, right? If the gap is too small, the length of the air fuel ratio, right? In order to develop this flame nucleus is narrow or reduced, right? So the length of the air fuel ratio is narrower if you have a too small gap here on the spark plug. Okay. This graph show you the electrode gap, the length of the electrode gap, right? With the change of the equivalent ratio here for different compression ratio. For different compression ratio here, you can see that if we go for higher compression ratio, right, start from 5, 6, and 8 here, right, higher and higher compression ratio on the same equivalent ratio, it means you require a smaller electrode gap here. Okay, so engine with higher compression ratio, the gap have to be small. Okay, now if you look at the equivalent ratio here, right, if you go for a lean mixtures, right, this is a stoichiometric line. If you go for a lean mixture, the equivalent ratio less than 1, right? Leaner and leaner mixtures require that for that engine to have what? A higher electrode gap, right? So that engine need a higher electrode gap here. Right? But for least mixtures, right? For this mixture here, right? The electrode gap is getting smaller and smaller, right? Until if it's starting to reach, then the electrode gap have to increase, right? So for this mixture, there are two characteristics for the length of the electrode gap, right? If you are not too rich, right, the electrode gap can be small. But if you are too rich, the electrode gap have to be wider. Okay. But for the lean mixture, there is only one characteristic, that if you go for lean, the electrode gap have to be wider. Okay. And also for higher compression ratio, the electrode gap have to be smaller. Okay. This graph show you the ignition temperatures. The ignition temperature versus the equivalent ratio here. Okay. So you can see that if you go for stoichiometric ratio, right, there is a lot of chance that you will get the maximum ignition temperatures, right, in here. But if you go for lean or you go for rich, the maximum ignition temperatures start to reduce, right? Too lean and too rich, especially in here, right? Your electrode gap have to be wider, right? Okay. And if your ignition temperatures is not that high, right, it's gonna be difficult for your combustions to happen, right? Because during ignition lag state, if you remember, we have to heat up the fuels until the temperature reach to the level that it can be self-sustained. Okay, ignition, the combustion can be self-sustained. Okay. Okay. The top graph here, the top one here, I give you the time for the ignition lag, right, versus the equivalent ratio here, right? So you can see that for a near stoichiometric ratio here, right, the time for the ignition lag is shorter, right? So combustion happen faster, right? So if you have the ignition lag time small, That means the combustion can happen earlier, right, or faster here. Okay, so during the stoichiometric ratio, right? And if you go for too lean and too rich mixture, right, you need more time for the ignition lag state. Right? So that means you don't have a fast combustion that happen. Okay, the combustion have to be delayed, right? Because the time for the ignition lag is bigger. Okay. Okay. So this one show you that the time of the ignition lag also depend on the temperatures, right? Because if you get higher and higher temperatures, the time for the ignition lag is smaller, right? Which is good. Okay, and this is the same as when you have the low electrode gap that compare with that at the stoichiometric ratio, right? The same as this one, right? When you go for stoichiometric ratio here, right? You have the shorter time for the ignition lag state here, right? So higher temperature that happen result in a shorter time for the ignition lag state here. Okay. That is the first engine variable, the electrode gap. Right here. The second variable that have on the ignition lag state is the turbulence. The turbulence. Right. Okay, we know that turbulence is directly proportional to the engine speed. Right. So if we go for higher engine speed, we expect to have higher turbulence. But the increase in the engine speed does not affect much on the ignition lag state. That is measured in milliseconds. What does it mean here? It means when we talk about the engine speed, we talk about in the unit of round per minute. Right. We talk about minutes on the time scale. But when we talk about the ignition lag state, our time scale is in milliseconds, which is very, very small, or that means it's very, very fast, right? So the effect from increasing the engine speed cannot catch up with what happened during the ignition lag state. That's what it means, right? Since it cannot catch up the turbulence that happened, right? Even though it happened, the effects that stems from the turbulence to the ignition lag state here does not in time for that ignition lag to take the effects from the turbulence in order to help itself. No time for that, right? Because ignition lag happen very, very fast in the period of milliseconds, right? So it is the time problem that the turbulence, even though by common sense is good, but the time for sending that effect from the turbulence to the ignition lag state here is not in time for ignition lag state to take the benefit from the turbulence that happened. Okay, that's why it does not affect much the ignition lag state here because of this. Okay, so time is a factor here. Okay. Okay, so that is the effect on engine variable on the first state of normal combustion. Right. We have the electrode gap. Right. We see how the electrode gap vary with the equivalent ratio, with the compression ratio, with the temperature, with the lean or rich mixtures. Okay. How about the second state of normal combustions? Right. What are the engine variables that have the effects on the flame propagation state, which is the second state in the normal combustions? The first one, the first variable is the air fuel ratio. Right? This air fuel ratio or the mixture compositions, right, has a very significant influence on the frame speed. Right? The key point on the frame propagation state is how fast that the frame can travel, right? The speed of the frame. This is the key parameter for the second state in normal combustion. And air fuel ratio has a very significant effect on this frame speed here, right? Why? Why frame speed is so important? Because if we can have the highest frame speed, right, that means what? That means we have the minimum time for complete combustions. And if we can have the minimum time for complete combustions, our peak pressure again, right? Our peak pressure, right, can happen closer to the top dead center. Right? So if we can go for high and high frame speed, it's good because of that. And how can we obtain the highest frame speed here? Right? The highest frame speed can be obtained with somewhat, I said somewhat here, richer mixtures. Right? The word somewhat give us a sense that there have to be a cap on something, right? Not go on forever, right? So how rich mixture that we can have in order to get the highest frame speed here? They said it's not more than 10% rich, not more than 10% rich. Right? If you go for above this number, you don't get the highest frame speed velocity here. Okay, so if you get the highest frame velocity, you can have a higher rate of burning happen. Okay. Okay. This graph show you, right, the frame speed versus the equivalent ratio here, right, for two fuel air mixtures. Right. The first one is the ethylene mixed with the air. The second one is acetylene mixed with the air here. Right. So you can see that on these two graphs, if your mixture is made leaner or richer, higher than 10%, the frame speed will decrease. Right? And if the frame speed decrease, right, in the case of lean mixture, it means you have less thermal energy is released from the fuel because the frame speed decrease. Right? Reaction happens slowly. You have less thermal energy released from that mixtures. And the result is you have lower frame temperatures. Right? You get lower temperature. Now, in case for a very least mixtures, right? Another problem happen because for the least mixture, it will lead to the incomplete combustion. Right? That result in the same thing, less thermal energy release. So both lean and least mixture, too lean and too least mixture, the result is the same, that you get less thermal energy release. But the cost that make less thermal energy release happen is different. In case of lean mixture, it's less because of lower frame temperatures that happen due to a lower frame speed. Right. For least mixture, you have less thermal energy release because incomplete combustion that happen due to lower frame speed. Yeah. So if you look at on the PV diagram, right, the complete cycle, you can see that if you go for rich, you have higher thermal energy resulting in terms of work because work represented by the enclosed area here, right? And for stoichiometric, you have smaller, and the smallest one happen when you go for lean here. Okay. And For this one, right, is another indicator diagram, but make the plot between the pressure and the crank angle here. Right. So if you have a lean mixtures, too lean, frame speed decrease. This is the point where you have maximum pressure. Right. It's far away from the top dead center. Right. But if you go for stoichiometric, you have closer to the top dead center for the peak pressure here. Right. And for least, right, you still further away, but not much, right, as in the lean mixture, right, for the peak pressure here. Okay. So this will give you an understanding on the equivalent ratio that have the effects on the frame velocity, and the frame velocity result in the peak pressures as shown in here. Okay. So that is about the fuel air ratio on the second state of normal combustions, right, to lean or to rich and stoichiometric. Right. The second engine variable is on the compression ratio. Right. It's about the compression ratio. Right. A higher compression ratio can increase the pressure and the temperature of the working mixtures. Right. So if the pressure and temperature of the working mixture increase, right, that means the ignition lag state needs shorter time, right? Because the mixtures already have high pressure, already have high temperatures, right? So the initial phase of combustion can happen faster, right? The initial phase of combustion here can happen faster. And that means what? You don't need to ignite earlier, too much earlier. Or in other words, you can have a less ignition advance. Right? You can ignite the fuel closer to the top dead center. That's what it means if you go for a higher compression ratio here, because the temperature and the pressure of the mixture already high. Right? So the initial compressions, right, or the initial phase of combustion, not compression, the initial phase of combustion can happen faster. Okay. Okay. The high pressure and high temperature of the compressed mixture that happen, right, also speed up. Okay, this is what already mentioned. It can speed up the second phase of the combustion or the flame propagation state here, right? Okay. Another advantage due to the increased compression ratio is that we can reduce the amount of the clearance volume, right? And that means the density of the cylinder gas increase during burning, right? Because the clearance volume reduced, higher compression ratio happens, the density of the gas inside the cylinder increase, right? And it increased during burning or during combustions, right? So that means the peak pressure and temperature increase. And if the peak pressure and peak temperature increase, the amount of time that needs for complete combustion can be reduced, right? So in overall, the engine that have a higher compression ratio will have a higher frame speed, right? And because of higher frame speed, we have less time for combustion, right? And less time for combustion good because we can have peak pressure near the top dead center. Okay. And this is show you here what I just mentioned. Okay. Right. For compression ratio equal to 4, right, the peak pressure happen here. Right. The peak pressure happen here. Okay. This is the top dead center. This is the line for the top dead center here. Right. All of these three compression ratio here, right, we do it on the same ignition start here. The ignition for these three different compression ratio happen at the same crank angles. right? But because of different compression ratio that show right here, the peak pressure location is different. Right? For higher compression ratio, here you can see that the peak pressure here happen very close to the top dead center. Right? For lower one, it moves away from the top dead center, right? As you see here, okay, further away from the top dead center here. Okay, so higher compression ratio give us the peak pressure near the top dead center here. Okay, so that is the effects on the second engine variable, the compression ratio. Okay, the third one is on the intake pressure and temperature. In fact, we do talk a little bit about this in the second parameter already. Okay, but we will talk more on here. Right? The intake pressure and temperature. Right? Increase in intake pressure and temperatures help increasing the frame speed. Right? Because you have a higher initial pressure and temperature, and this will help to form a better homogeneous air fuel mixture. Right? So the air fuel can mix with each other better because of higher intake pressure and higher intake temperatures. Right? And when you have a better homogeneous air fuel mixture, it means the frame speed can be increased. The frame speed can be increased, right? And the overall result of this can make possible because what? Because of the final one is you will get an overall increase in the density of the charge, right? Increase in pressure, increase in temperature, you have a better homogeneous of air fuel mixtures. All of this happen because you have a higher density of the mixtures. Number 4, engine variable is on the engine load, right? The load that acting on the engine. Okay, if you increase the engine load, the engine will respond by what? Increase the cycle pressure. If it can support that load on the condition that the engine can support the load that increase, right? So if you increase the load to the engine, okay, the engine will increase the cycle pressure. And if the cycle pressure increase, the frame speed increase, right? So on the condition that the engine can support the load, let's look at how we can make this engine to support the load, right? It can support this loading because of the increase in the throttle opening, right? We have to open more and more on the throttle valve, right? When the load increase, right? So on the condition that the engine can receive the load, it means we can still open the throttle valve wider and wider. And this will help the cylinder get filled to a higher density. That means more and more air coming in, right? And when more air coming in, it draw more fuel coming in order to keep the air fuel ratio the same, right? So more amount of air mixture flowing in the cylinder. Okay. Now, if the load is decreased, right? Now, if the load is decreased, before that the load increased, more fuel air mixture flowing in, so more combustion happen, the frame speed increase. Okay. Now, in the case that the load is decreased by throttling, throttling means we reduce the the opening of the throttle valve, right? We make it less opening. This is what we mean throttling. Okay, so the load, if the load decrease because we reduce the opening of the valve here, if the initial and the final compression pressure decrease, right? This is what happened here, and that means what? our working mixture, right, is more dilute. Right? Our working mixture is more dilute here, or the dilution of the working mixture increase. Right? So what happened is the smooth development of the self-propagating nucleus or frame that usually happen, right, will now become unsteady. Right? So we have the unsteady development of the self-propagation nucleus or frame. Right? So you can see, if you look at the combustion, if you can look at the combustion chambers, right, the frame, instead of travel smoothly, right, it start to fluctuating or unsteady happen to the frame, right? And this will even more difficult if you still keep decreasing the engine load, right? So increasing the engine load does not do any harm to our combustions, because the engine, if it can still respond to that load, right, it do nothing, no harm to our combustion. But decreasing the load, right, our frame state will get a total effects from that decreasing the load, because the frame start to become unsteady. Okay. So what happens when our frame start to become unsteady? You have poor combustions happen. You have poor combustion happen. So that's why most of the SI engine require the additive to their fuel. Right? So the gasoline fuel need additive or needs the mixture enrichment. Right? We have to add something in the fuels, the gasoline fuels. Right? This is to help our engine when it is unloading. Right? The frame is not steady. Right? Poor combustion happen when the engine is unloading. Right? To help the engine, right, escape from these situations, we have to add something in our fuel. Right? But adding something which we call the additive, right, into the gasoline fuel, right, it helps engine, even though it helps engine, but it also creates another problem. And that problem is what? The weightage of the fuel itself, the discharge of the unburned hydrocarbon, and the product of incomplete combustion that might happen, such as the carbon monoxide, right, that might happen. Right? So that means what? If you want to add the additive in your gasoline fuel, because of this, that help the engine during unloading, you cannot add more and more or whatever you like, right, for the additive into the gasoline fuel. There must be a cap. There must be a cap on the amount of the additive that you put into the fuel. Okay, so this is the point. Right? It doesn't mean that additive is always good. Right? There is a certain limit that you have to add this additive into the gasoline fuel, because if you add it too much, it will lead to all of this problem. You have problem about why your engine consume a lot of fuels, right? Why the smoke come out is black, right? The exhaust gas that come out is black, highly smoke, right? And in that exhaust gas, you have the product of incomplete combustion happen. Okay. Number 5, engine variable on the second state of normal combustion is the turbulence. Right? In general, we know that turbulence play a very vital role in the combustion phenomenon. Right? The frame speed is low. in the non-turbulent situations. Right? If we have non-turbulent flow, right, the frame speed is low. Right? Why the frame speed is low in non-turbulence? Right? Because of we're gonna have an additional physical mixing of the burning and the unburned particle at the frame fronts. Right? At the frame fronts, right, the frame travel in order to burn the fuel in front of the frame. This is what happened, right? So in front of the frame, we have the unburned fuel air mixtures. Remember, we discharge the fuel air mixture into the chamber, our cylinder, so it goes throughout our chamber, right? So the frame have to travel in order to catch up with all of this fuel air mixture and burn it. Now, if the frame speed is too slow, right, that means there is more time for this burning and unburned particles, right, to do the mixing all together again, right? So now this time is the mixing of burn and unburned, right? Okay, that happened, right? Okay, and that means what? If this happen, right, if this mixing happen, it will result in the increase of the rate of contact, right? Because it's mixing, so you have a high rate of contact between these two, right? And that will speed up the chemical reactions. But this chemical reaction that speeds up will lead to the incomplete combustion, because it's the burning of the mixture between the particle that already burned and the particle that is not burned, right? So the chemical reaction that happen will give you an incomplete combustion. Okay. Now that happen if the non-turbulent situation happen in your cylinders. The frame speed reduced, you have the mixing of burned and unburned particle that lead to the incomplete combustions. Now, if the turbulent happen, right, the turbulent motions of the mixtures will intensify the process of the heat transfer and also the mixing of the burned and unburned portion in the frame fronts. Right? So the turbulence that happen, right, will speed up the process of the heat transfer and also the mixing process of the burned and unburned portions. Right? So the frame speed increase, right? Because more heat go into that mixing, right? So when it reacts, right, the frame speed increase. Right? This turbulence, right, that we would like to have in the incoming mixtures, right, we can get it. When? During the admissions of the fuel air mixtures. Right? When at the time that we start to admit the fuel air mixture, right, into the cylinders or the combustion chamber, right, we can create the turbulence to that fuel air mixture during that time. By what? By letting the fuel air mixture to flow through a comparatively narrow section of the intake pipe. If you remember, right, we have a venturi. Right? So we let our air fuel mixture flow through the venturi, right, in order to create the turbulence for the incoming flow before it go into the cylinder. And also the second turbulence happen when it flow past through the valve opening, right? So the first turbulence happen at the narrow section, which is the venturi. The second turbulence happen when it flow past to the intake valve openings, right? All of this happen in the intake stroke. So this is the way that we can create the turbulence, right? Yeah. So the increase of the frame speed because of the turbulence will help reduce the combustion duration, right? Everything lead to reduce the amount of time for the combustion to finish. Okay. And apart from this, by increasing of the frame speed, it will reduce the chance for abnormal combustion to happen. Okay, so turbulence reduce the time for the complete combustion and also reduce the chance for the abnormal combustion to happen. But it's always happen like this, right? We cannot go too far left and too far right. This is what happened in the internal combustion engines. Too excessive turbulence. If we have too excessive turbulence, it will thus cool the flame generated. Right? If turbulence is happen too much, right, the flame temperature reduce, and that means what? The flame propagations also reduce. Right? We want the flame to propagate fast, and we want also the flame temperature to go high, because this will speed up the chemical reaction, especially at the flame front, right? Because the flame have to catching up with the unburned particles here in the cylinders. If we have too much turbulence, the flame temperature go down, the flame speed reduce, and the problem is what? You will hear a loud and noisy operations of the engine. This is the result that happened, right? So moderate turbulence is always desirable for us, right? Moderate turbulence is always the thing that we would like to have, because for moderate turbulence, it will help accelerate the chemical reactions. It can help reduce the time required for the ignition lag state here. It will increase the flame propagations, and it will allow the weak mixture to burn efficiently. Okay. So moderate turbulence is the thing that we want. So it depends on how you create the turbulence in order to keep the level of the turbulence, right, not too much and not too low. Okay. That is the number 5 engine variable. How about number 6 on for the engine variable on the second state of the normal combustion? Right. Number 6 is the engine speed. Okay, the engine speed. Right. We know that the flame speed increase almost linearly with the engine speed. Right. Right. If we have higher engine speed, the flame speed increase, because the increase in the engine speed will increase the amount of the turbulence or the level of the turbulence inside the cylinder. Okay, so if the flame speed increase, the time required for the flame to transfer or to travel across the combustion space would be reduced in half. So we just have half of the time for the flame to travel across the combustion space. Right? On the case that if our engine speed is double, right? Because if our engine is double, let's say that the flame speed is also double, so the time for the flame speed from the flame to travel across the combustion space or the combustion chamber will be reduced in half. Okay, but as I already mentioned, earlier, okay, no matter how big is your engine is, what size of your engine, the crank angle is still 360 in 1 revolution per minute, right? So by doubling the engine speed and then half of the original time that we can receive by doubling the engine speed. These two, even though it happened, but it still gives the same number of crank degree for the frame propagation, right? Okay, 360 is still there. Right? No matter that your frame speed increase and the time is reduced by half. Right? The crank degree is still the same for the frame to propagate. Right? That means the same distance for the frame to propagate. That is. Right? Because crank angle represents the distance. Okay. So the crank angle required for the frame propagation during the entire phase of combustion will remain nearly constant at all speed here. Okay. The crank angle, the amount of the crank angle required for the frame to travel during the entire phase of the combustion still nearly constant or remain the same for every speed for the same engine, right? For the same engine, because for the same engine you have the same cylinders, right? And you can run this engine for different speed, but for different speed the crank angle have to travel what, 360 round per second, round 360 per 1 round of revolutions, right? So this is an important characteristic of all the SI engines. Okay, so you increase the engine speed, you increase the frame speed, but the crank angle required for combustion still the same. Okay. Okay. Number 7, the engine side, right, that have the effects on the second state of normal combustions. Right. In general, like if you go for the similar engine design or similar design of the engines, right, no matter what size it is, right, if that engine come out from the same family, right, it always have the same piston speed. This is the fact. Right. Not depend on the size. Everything is the same. It's just bigger or smaller. Right. This family of the engine, right, always have the same piston speed. Right. Why? Why we can make the engine on the same design with different size to have the same piston speed. We can do this by designing the small engine. Right? When we talk about the small engine, that means the stroke length is small. Right? We design this small engine to run with a larger RPM. Right? And when we design a large engine that have a large stroke length, right, we design it to run at a smaller RPM. Right? Because if you look at the formula for the piston speed here, right, it depends on the stroke and depends on the engine speed. For large stroke, you have to use smaller RPM. For small stroke, you have to use higher RPM in order to keep the piston speed the same, right? If you use similar design for these engines. Okay. And because they have the same piston speed here, right, for the similar design engine, the inlet velocity, the degree of turbulence, and the frame velocity are nearly the same in the same design engine, no matter what size it is. Right, this is what happened. Everything is the same, no matter how big the engine is, on the condition that they have the same design. Right. The only difference is what? The time. The only difference is the time. Okay. In large engine, right, the time required to have a complete combustion is more, right, because the frame have to travel a longer distance in the cylinder, right? Because you have a bigger cylinder for the large engine, So you have longer distance to travel for the frame. Yeah, right. So that means what? Since large engine, time is more. Right. So when you design a large engine, right, you have to design it to run at a lower RPM. Right. With lower RPM running for the large engine, more time that you require to have, right, can be obtained, right, on the condition that you have the same crank angle duration as happened in the small engine. Right? So that everything here above here, the inlet velocity, degree of turbulence, and frame velocity are the same. Okay, so for large engine, right, it usually designed to run at a lower speed here because they have the same piston speed, but they require more time for the frame to propagate. So they need time, and that time can be obtained by letting them running at a low speed. Right? So that is why all of the large engines, big size engines, right, you can see that it run at a lower RPM, yeah, because of this, on the condition that they are the same design engine. Okay, if they are the same design engines, right, large engine will run at lower speed, small engine will run at the higher speed, because they want everything to happen the same inside. The combustion, right, the combustion phenomena that happen in that engine have to be the same, right, because they come in from the same design, only the size that difference. Right? They don't want the size difference to make something that matter to the combustion phenomena. Right? So they run the engine with different speed. Yeah. Okay. So that is for the normal combustions. Okay. Any question for that normal combustion so far? มีคำถามอะไรไหม? Hello, any questions for the normal combustions? Right, we have three states of combustions happen. No? Hello? Hello, ได้ยินหรือเปล่า? Hello, hello? ไม่มีเหรอ? ยินครับ โอ้โหเงียบเลยเว้ยหลับเลยเปล่าเนี่ยฮะหลับเลยดิ ฮะไม่มีคำนวณนี่ฟังหลับเลยนะหรือว่าฟังไม่รู้เรื่องวะเนี่ย okay, so if no question, we continue on the abnormal combustions. Okay, the normal combustion is something that we would like to happen to our engines, right? But we still have to talk about something that we would not want to happen. Okay, that is the abnormal combustions. Right? So for the normal combustion, right, the picture that you can see is shown here. Right, the frame that initiated by the spark will travel across the combustion chamber. Right, across like this combustion chamber in a fairly uniform manner. Right, everything goes smooth like this. Start from the spark plug and the frame travel like this. Right, along the way that it travel, right, you can see that the frame front here, you can see the frame front here, get the effects from compressions, right, from the frame that travel behind. Right, so this combustion due to the frame front here, right, will result in the temperature increase in these regions, and this temperature increase in this region, right, come out not only because of the mechanical compressions, right, it come out because of the compression due to the frame speed that come behind. Right, so the temperature in the frame front in this region here can be increased because of this. Right, but if the temperature increase here, right, does not increase up to the level of the cell ignition temperature, the normal combustion happens. Right. So the problem is the temperature here, not in here, the temperature here, right? The mixture here already have the temperature increase due to compression stroke, but they do have additional temperature increase because of the frame that travel behind it. Right? But as long as the temperature increase in here does not go up to the cell ignition temperatures, we still have the normal combustion happen, and our pressure will look smoothly like this. Right? But right, this rarely occur in a real engines without some trace of auto ignition appearing. What does it mean here? It means when you look at something that so smooth like this happen, you cannot be sure that your engine is running on the normal combustion because it rarely happen, right? But fortunately that if you look closer, right, the auto ignition that happen is very light, not very hard, or the auto ignition that happen is so soft. That's what they said, without some trace of auto ignition appearing. Right? The auto ignition happen, but the effects from this auto ignition is so small. That is it. Okay. Right. You cannot say that you have a complete normal combustion for every engine. Right? No complete normal combustion. It rarely occurs. Okay. But fortunately, auto ignition that happen is so small. Right? But under certain operating conditions, this auto ignition effects might be last. Right? If the combustions, right, happen to deviate from its normal course in under certain operating conditions. Right? If that combustion happen to deviate from its normal course, this will lead to the loss of the engine performance and the possibility that our engine can be damaged. Right? This type of combustion that happen, we call it the abnormal combustion or knocking combustions. Right? And the results from this abnormal combustion is what? The engine will have a loss of powers. Right? There will be a recurring of pre-ignitions. That means pre-ignition happen not only once, but it may be twice, 3 times, and so on. This is what we mean, recurring pre-ignitions. And the last one is the mechanical damage to the engine because the piston does not move according to what is supposed to be moved. Okay. So how this abnormal combustion happen? How this abnormal combustion happen, right? After ignition happen, as we already mentioned, the flame front will travel across the combustion chamber like this. Right? The end gas here, right? These two portions, which is the gas or the heat of the flame front, right, will receive heat from the compression or the expanding gas. Remember, the combustion happened during the expansion stroke, right? So the gas start to expand, and due to that expansions of that gas, right, compression happen. So this is the first heat that the end gas will receive. the compression of the expanding gas. Okay, the second heat that this end gas receives is from the radiations from the advancing flame front, right? Because flame front here keep traveling, right? So the radiations from this flame front go. So the end gas receive the radiation heat also. So these two heat result in what? The end gas temperatures and the end gas density increase. Okay. So if the increased temperature go beyond the cell ignition temperature, right? And this unburned gas, the end gas here is still unburned, right? Remain at and above, right? At or above this temperature for a period of time that equal to or greater than the delay period, right? The auto ignition can occur. Remember, right? At the beginning, when you start the engine, this thing might not occur, right? But when the engine keep going on and going on, you have heat inside the cylinders, right? So all the chance for auto ignition, right, can happen because of this, right? That's what they mentioned here, right? That the temperature of the end gas go up beyond the ignition temperatures, and this unburned gas that is still not receiving the flame fronts remain at this temperature or above this temperature for a period of time equal to or greater than the delay period. Right? The spontaneous ignitions will occur, and it happens at various locations. Right? So if it stays at that temperature for a time equal to the delay period, right? The time equal to the delay period mean what? The normal ignition happen and this gas also ignite. This is what it means. The time equal to the same delay, equal to the delay period, right? So when ignition, normal ignition happen, this end gas also ignite. So we have twice ignition happen at the same time, or greater than the delay period. That means the normal ignition happen, and then after that, right, this end gas ignite itself. Right? So all this will result in what? The auto ignition or spontaneous ignitions. Right? And it happens in various locations because the end gas is in front of the flame fronts, right, and is distributed, right, throughout the combustion chamber. And if you look at the pressure and the crank angle here, right, this is what you see. The pressure now is not smooth. You see the pressure pulse happen here, several of this. Okay, so this process of auto ignition will lead to the engine knocks. Right? The engine will knock because of, instead of having just one flame front going forward, you have another flame front due to this ignition happen. And this another flame front will start traveling in the opposite direction, right, to the main flame front. So one flame front going forward, another flame front going backward. And when these two flame fronts collide with each other, right, a severe pressure pulse is generated. That's why you see this kind of pressure pulse here, because these two flame fronts collide with each other. Okay, and you will hear an audible sound that we call a knock happen. Okay, but if the end gas does not reach its self-ignition temperature, the combustion will stay normal. Right? The combustion will stay normal. Okay, so something that should be noted is that the onset of the knocking, right, or the starting of the knocking is very much dependent on the property of the fuel, right? Because the key point is if the unburned mixture does not reach its auto ignition temperature, right, there will be no knocking. This is the key point, right? And also another one is if the ignition lag period is longer than the time required for the flame front to burn through the unburned mixture, there will be no knocking. Right? So there are two key points. Right? There are two key points. Okay, that will related to the property of the fuel, because these two key points will lead to no knocking condition. The first one is if the temperature is not go up to the self ignition temperature, right? There is no knocking. Another one is if the ignition lag period is longer than the time for the flame to travel and burn the unburned mixture, right? There will be no knocking. Okay, so these two key points lead to the property of the fuel, right? That is what the property of the SI engine fuel have to have what a high auto ignition temperatures and can provide a long ignition lag time, a long ignition lag time. Right? If our SI engine fuel have these two properties, right? High auto ignition temperature and can help the engine to have a long ignition lag time, right? Our engine will have no knocking condition happen. Okay, so this is to avoid the detonation. Right? Some people use detonation instead of knocking. They are the same. Okay, so all the SI fuel, SI engine fuel, they will add the additive here in order to lift up the auto ignition temperature and provide a longer ignition lag time here to avoid the knocking. Okay. Okay. Effect of the knock. Right? If knock happen, what will happen after the knock? First, noise and roughness. Right? The roughness operation of the engine. Right? You can hear the engine rattling sound. The rattling sound of the engine happen. Okay. The second one is the mechanical damage, such as what? Increase in the engine wear, increase in the damage for the cylinder head and the valve, right? The cylinder head and the valve may have may be pitted. Pitted means the cylinder head and valve may have several small holes that happen on the surface. Right? This is the mechanical damage that happen. Right? You may have the carbon deposit in the cylinders, right? And this result in the increase of heat transfer. Okay, right? Heat transfer increase too much. Okay, decrease in the power output because of the increase in the amount of heat transfer, and also the efficiency reduced. Okay, you have pre-ignitions happen, that combustion occur before the spark. Right? So these are all the effects of the NOx that happen to the engine. Okay. Let's look at the engine variable effects on the NOx, right? Because we want to prevent the NOx in the SI engines, right? We can use a better property of the fuel to prevent the NOx, right? But we can do also, we can also do some other things to prevent the NOx, right? To prevent the NOx in the SI engine, right? The end gas should have what? Low temperature, low density, long ignition delay, non-reactive combustions, right? These are all the conditions that the end gas should have, right? 4 conditions altogether, right? But the problem is what? We never operate the engine on one single conditions. Right? When we operate the engine, we operate it on several conditions. Right? So the effects of the engine condition change, right, right, may be reflected by more than one of the above variables. Right? That means when we change the condition of the engines, right, the chance of NOx may happen, because instead of keep controlling just either one of these, right, we have to keep controlling more than one of these variables, because more than one of these variables might affect to the engine condition when the engine condition changes. Okay. So first, let's look at the temperature factors. Right. The temperature of the unburned mixtures, that we have to keep it under the auto ignition temperature, can be increased by the following factors, right, under the condition of the engine change, right? And if the temperature of the unburned mixture increase under the condition that of the engine change or the engine condition change, right, it will lead to a more chance for engine knocking, right? Such as what? Such as if the condition change, the engine condition change by increasing the compression ratio, right? So you increase the compression ratio, more chance for the temperature of the unburned mixture to increase, right? Or you do supercharging, right? You have a turbo that charge the air into the cylinder, so the air that flow in have higher pressure than the atmospheric pressures, right? So there is a chance for the temperature of the unburned mixture to increase. You increase the inlet temperature. This is so obvious, right? That means the unburned mixture temperature increase. You increase the coolant temperature, so less amount of heat that can be transferred from the engine. Right? So the temperature of the unburned mixture increase. You increasing the load. Right? You advancing the spark. Right? You do the spark or you do the ignition earlier, too much earlier. Right? You increase the temperature of the cylinder and the combustion chamber wall. Okay. So all this, right, happen along the way that the engine condition changes, and all of this will lead to the increase of the unburned mixture temperature, and that will lead to more chance for NOx to happen. Okay, so that is the temperature factor. The second factor is about the density factor, right? For the density factor, right? Increasing the density by any of these following method will increase the possibility of NOx, right? Increasing the load, right? The engine responds on the increasing of the load, right, by increasing the density of the mixture. Increasing the compression ratio, you have higher pressure, you have higher temperature, your density increase. Supercharging, right, increasing the pressure, density increase. Advancing the spark, you do the spark earlier, right? So the fuel get the energy earlier, the density become increased. Okay. So that is the second factors that lead to more chance of NOx. The time factor, the third one, time factor. If you increase the exposure time of the unburned mixture to auto ignitions by any of the following factors, it will increase the tendency to NOx, right? Increasing the distance of the flame travel, right? Higher distance, so more time, right? Because you increase the distance of the flame travel, that means the flame need more time. So when it's more time, there is more exposure time for the unburned mixture, right, to go up to auto ignitions. Decreasing the turbulence of mixture, right? That means you reduce the chemical reaction rate because you decrease the turbulence of the mixture. The chemical reaction rate is reduced, or the chemical reaction become slower, right? Become slow. Okay. Decreasing the speed of the engines. You decrease what? The frame speed, right? So you decrease the frame speed. So more time for this unburned mixture to receive the energy and increase its cell temperature up to the auto ignition temperature. Right? So this is the time factors that affects the NOx. Okay. The last variable is on the compositions, right? Composition of the fuel mixtures, fuel air mixtures. Right? The possibility of the NOx in the air engine can be decreased. Okay, so this one they talk about decreasing the chance to have NOx in the SI engine by what? Increasing the octane rating of the fuel, right? So you have the better property of the fuel to help decreasing the chance of NOx. Right? Using either leach or lean mixtures can also help reducing the NOx. Or stratifying the mixtures. Right? You don't go for homogeneous of the mixture. Right? You go for heterogeneous. Right? That's what we call stratifying the mixtures. Increasing the humidity of the entering air. Right? You increase water into the coming air, right? In order to what? To receive the heat. Right? So the temperature reduce. Right? When temperature reduce, you have less chance for NOx. Okay, so this is about factor that can reduce the NOx, right? The chance to have the NOx. Okay. Okay. Since we talk about the fuel property, so it's a good time to talk about the octane number here. Right? Everybody know about the octane numbers. Right? Okay. What is the highest octane number used in Thailand for the gasoline engine? Any student know what is the highest octane number used in Thailand for our gasoline fuel? รู้ไหม Hello
ไม่รู้ครับ
You don't know the octane numbers of the fuel, the gasoline fuel in Thailand? Right? You see the letter 95? Have you ever seen the letter 95? When you filling the oil in your car, you have to say, I want the gasohol 95, gasohol 91, right? That number represents the octane numbers, okay? So the anti-NOx value of the SI fuel or the gasoline fuel is measured in octane number rating, ONR, right? This octane number rating is set up by what? Comparing the NOx of the fuel under test, right, with that of a blend of the primary reference fuels, right? The primary reference fuel that we mentioned, right, is what? The first one is the isooctane fuel. This isooctane fuel is having a highly NOx resistant, right? It's the fuel that the chance to get knocked in the engine is very, very small, right? So this isooctane fuel, right, is rated as octane number 100, okay? Another primary reference fuel, we call it a normal heptane or N-heptane, right? For normal heptane, right, it can be knocked easily, right? Our engine can be knocked easily if we fill up our SI engine with this fuel, the normal heptane, right? So it is rated for 0 octane number, right? So we have 100 and we have 0. So in between of these two numbers, it is the mixtures of these two primary reference fuel, right? Right. So between these two, it depends on the proportions of these two primary reference fuels here. Okay, so that come the octane numbers, right? The octane number is defined as the percentage of the isooctane, which is have octane number 100 by volume in a mixture of the isooctane and N-heptanes, right? Which exactly match the knocking intensity of the given fuel in a standard engine under prescribed operating condition, right? So whenever you come up with the new formula for the fuels, the gasoline fuel, right, you have to compare your gasoline fuel with a standard blend of the isooctane and N-heptane in order to rate your octane number of your fuel. Okay, so this is the way they do it, right? Whenever you come up with the new gasoline fuel and you want to know how much octane number is your fuel, right? Your fuel might not use isooctane or N-heptane, right? You use other fuel, but whenever you come up with a new one, you have to compare with isooctane blend with the N-heptane, right? In order to rate your octane number fuel, your fuel octane number here. Okay, so by lowering the octane number, there is more possibility of the fuel to knock, right? Because 100 mean has to knock, right? So less number of the octane number lead to more knocks that can happen. Okay. So now, if we want to use the additive in order to prevent the knocks, right? Let's look at the influence of the fuel additive to prevent the knocks, right? Because using the fuel additive here, we can raise the octane number of the fuel. Okay. Using the fuel additive here, we can raise the octane number of the fuel. That is one way to do it. Another way is by using the refining method. Okay. You refine the fuels from the raw, from the petroleum oil, right? The raw oil here, right? You refine it, the good, use a good refining method. You can also come up with the higher octane number, but your fuel may be expensive if you do that. Okay, so instead of using the refining method here, which lead to the expensive fuel, right? People use the additive in order to raise the octane number, right? And this additive that fill in the fuel, it do what? It will control the surface ignition, right? The flame front surface. It can control the flame front surface not be too wide, too large. Okay, it can reduce the spark plug fouling, right? The spark plug fouling that happen to the spark plug. It can resist the gum formation that happen in the cylinders, right? This gum formation become the hot spot, and the auto ignition might happen because of this hot spot. It can prevent rust that happen because rust is mean oxidation happen, right? So when it happen to have chemical reaction, right? And if you have rust inside your cylinder, right? That means you have more chance to have another chemical oxidation process happen, and this will lead to the NOx. Okay, so this additive tool is used to prevent all of this. Okay, it can reduce the carburetor icings, right? icing can lead to the knock, but now, as we mentioned, we no longer use the carburetor, right? Remove carburetor or injector deposit. Okay, the same, right? You inject the fuel, not all the fuel that completely come out from the injector. They might have some small molecule of the fuel that's still attached to the injector, and this become the deposit, right? And it another hotspot in here. Minimize the deposit in the intake system, right? Prevent the valve sticking, right? The valve not widely open, right? Because of there is some sticking happening to the valve here. Okay, so this additive do all of this to prevent the knocks, right? The most effective anti-knock agents are lead acryl. Lead acryl is the most effective one, and it's very cheap. But using the lead, right, will lead to the toxics that happen in the urban environment, right? So lead is banned, right, since 1970. So all of the fuel cannot use lead as an additive in order to increase the octane number. And because of that, right, because of that, start from 1970, right, we start to have an unleaded gasoline. The unleaded gasoline start to have that. And it's followed up by the use of the catalytic converter device, right, in order to control the emission, right. This emission have to be controlled because many countries come out with the law, right, in order to control the harmful pollutants in the environment. Okay, so the unleaded gasoline, right, start to use from 1970 because of this, right. So the expanding use of the unleaded fuel had increased the interest in other methods of increasing the octane number of the gasoline, right? Because the winner with it, the lead acryl here, right? Lead acryl here have been banned, right? People cannot use them to increase the octane number, right? So it's open a chance for other agents or other additive, right, to come into this market, such as what? Such as using the oxygenase, which is what? The alcohol and ether as a fuel additive to increase the octane rating, right? Instead of using lead, right? Now they use other additive here because lead is banned due to its toxic. Okay, so in the market nowadays, there are many laboratories that try to come up with a better additive here to increase the octane number, right, at a cheaper cost, right? Okay. Okay, so that is about the abnormal conditions that lead to the NOx that happen in the engine, and we can control the NOx by using the additive in the fuels here. How about the last one, the uncontrolled combustion for the SI engine, the uncontrolled combustion, right? Under certain conditions, right, the fuel air mixture can be ignited by the hotspot in the cylinder instead of the spark plug, right? So the uncontrolled combustion mainly happen because of the hotspot, right? The deposit that we left over in the cylinder, right? So it's different from the abnormal condition, right? That happen because the temperature increase above the cell ignition temperatures, right? But for the uncontrolled combustion, it happened because of the hotspot. Yeah, right. The hotspot. Where is the hotspot? It may be the spark plug insulator. It may be the electrode, right? It may be the combustion deposit. right? So that means the hotspot not only on the combustion deposit. In this case, it can be the insulator, it can be the electrode here. All of these are considered to be a hotspot. Now, if the ignition by hotspot occurs, if it occurs before the spark, then it is called pre-ignition. If it occurs after the ignition is switched off, then it is called running on, right? So it have two kinds of ignitions, pre-ignition and running on ignitions. Okay. Yeah. So if the ignition happen because of the combustion chamber deposit here, right? In which we sometimes call it the surface ignitions, right? We will have the event called the rumbling or rumble in engines, right? So the engine sound will change, right? And that sound we call is the rumbling or rumble in the engine, right? So it's like you hit what? You hit the drum. You hit the drum, right? You can hear this sound in the YouTube, right? You just type in rumble in the engines, right? There is one of the video in the YouTube that can help you to hear what is called the rumble sound in the engines. Okay, and this sound can be detected either by what? Hearing a continuous deep and resonant sound or hearing change in the engine noise. Right? If you want to detect by hearing, okay, and if you want to detect by the device, right? You can detect it by measuring the time of the peak pressure, the rate of the pressure rise, and also the frame font propagation time, right? So you can detect it by either hearing or using the device. Yeah. Okay, so that is for the combustion in the SI engines. Okay, any questions for the abnormal and uncontrolled combustions? มีคำถามอะไรไหมนะครับเผาไหม้ในเครื่องยนต์เบนซิน If not, then we take 10-minute break. Huh? Okay. Before we go for the combustion in the CI engine. โอเคนะ Hello.
โอเคครับ
งั้นเดี๋ยวwe come back at 11:20. Okay, about 11:20. Okay. คนเข้าคนออกโอเคต้องแชร์ใหม่เพราะมันขึ้นจออะไรไม่รู้โอเคโอเค okay so we will continue นะ okay everybody ready เห็นไหมทุกคนพร้อมไหมครับ
พร้อมครับ
โอเคนะอีก20 สไลด์ เยอะหน่อยนะแต่มันก็เป็นเรื่องที่คิดว่าควรจะพูดนะครับนะจะตัดก็ได้แต่ว่าอย่าดีกว่านะครับ okay so we will continue on the combustions for the CI engines right the diesel engines right so in general right the combustion in the CI engine start when the air is drawn during the intake stroke, right? And the temperature is high because of the high compression ratio, right? So after the air is drawn, the fuel is then sprayed into the combustion chamber, right? So together, the spray of the fuel and the air movement, right? These two, right, will distribute the fuel through the air, right? So fuel is spare, the air is movement, right? The air movement, right? The air move or flow, right? So the fuel can be distributed throughout the air here, right? And after that, the fuel ignites and burn, right? This happens as soon as the fuel is introduced, right? So the burning, the ignitions and burning happen as soon as the fuel is introduced because of the air high temperatures. Okay, so this is difference from the SI engines. Okay, so due to the heterogeneous content in the cylinder, right? Because for the CI engine, the air and fuel need not to premix with each other before introducing into the cylinder. So we have the heterogeneous content in the cylinder. Right? So the fuel air mixtures can be varied in different regions in the cylinder. So this is pictures of how the combustion in the CI engine happen. Right? And if you can take a look in the combustion chamber, right, of the CI engines, you will see this picture. Right? The thing that you notice is what? You can see that the frame length are different according to the time after ignitions, right? So let's see, look at this one. 0.4 millisecond after ignitions, right? You see the frame length is very short, right? And 3.2 millisecond after ignitions, you see the frame length like this, right? Or maybe you see the frame length like this, right? And then after, and then in the length of the combustion process, right? It's very, very short frame length here, right? So this happened in the CI engine due to the combustion phenomena that we just mentioned, right? You can see different frame length, right, happen in the combustion chamber. Okay, so it differs from the SI engines, right? That we have a uniform distributed of the frame here. Okay. How about the temperature distributions, right, for the CI engine? Right? This picture shows you the temperature distribution inside the cylinders, right? Where you have a highest temperature in the regions where combustion happen, right? This is the region of that we have a high temperatures, and the frame font is right here where we have a much lower temperatures that happen here. Okay, so you see the temperature difference across the combustion chamber, not the uniform one. Okay, for the CI engine, because we have heterogeneous content in the combustion chamber. Okay, and this graph show you three main parameters that happen in the combustion of the CI engine. The first one is the fuel injection flow rate, that represented by this dotted line here, right? And you see the net heat release rate, represented by this dark line, dark and black line here. Okay, and the last one is the cylinder pressure, represented by the red color here. Okay, in this diagram here, okay, let's first talk on the fuel injection flow rate. Okay, the fuel injection start here, right, where you see that the amount of the fuel injection rate go up very quickly, right, in a very short distance of the crank angle traveling. Okay, so it happened, we inject the fuel, right, immediately here. Okay, and then after that we reduce the amount of injections, and then increase the amount of injection again, right? Increase it immediately again, and then reduce, and then increase a little bit here, but use longer time here, right? So we have shorter time to quickly increase the amount of injections here, right? You can see here, and longer time to reduce the amount of injections, and longer time to increase the amount of injections, right? And after that, we reduce the amount of injection until finish injection here. Okay, so this is what happened, like during this is what happened, or this is the way we inject the fuel into the cylinders, right? So you can see that we have multiple injection of the fuel here, right? For this graph, you see 3 injections per combustion cylinder here. Okay, so how about the heat transfer, the heat release here? Okay, so at the very beginning, when you inject the fuel, you don't have the heat transfer out from the engine. In fact, you see the heat transfer into the cylinder, right? Because the sign of the heat is negative, right, at the time you start to inject the fuel. And then up to here now, right, you can see that you know that the start of combustion happen here, because you start to see the heat release out from your combustion chamber, and it go up very, very quickly to a high amount here, right? And after that, the amount of heat release, right, reduce, the amount of heat transfer reduce, right? And then increase a little bit before it die out here, right? So this is what happened to the heat release rate here, right? So it increased rapidly, right, at the start of the combustions, right? And then it reduced rapidly also, right, just a short while after combustion happened, right? And after that, it increased a little bit and start to dry out here, right? How about the pressure? The pressure, right? Along this line here, you know that it's no combustions, right? No combustion, because it's still on the motoring curve. And then when combustion happens, again, you see the rise of the pressures until it go up to the maximum pressure here. And after that, it decreases, right? And again, the maximum pressure is away from the top dead center, same as the SI engine. Okay. So this is the characteristic of 3 main parameters, right, during combustions, right? The fuel injection, the net heat release rate, and the cylinder pressure. Okay. So since the combustion depend on the oxygen in the air, right? So for the CI engine, right, it will require more excess air or the lean mixture than the SI engine in order to achieve the high efficiency and low smoke level here, right? Because the air and fuel does not pre-mix with each other, right? So it want to make sure that throughout the combustion chamber, they have oxygen throughout, right? So it needs lean mixtures to ensure that they have enough oxygen to burn all the fuel that they introduce into the combustion chambers. Okay. The combustion in the CI engine have 4 states altogether, right? For SI engine, we have 3 states of combustion, but for the CI engine, there are 4 states of combustions, right? The first is the same, right? But they call it the ignition delay period, right? The ignition delay period is where the combustion still not happen, right? Just a short time here. This is the ignition delay period. Right? You don't see the visible pressure rise, right? Same as in the SI engine, but the fuel is injected through the nozzle. There is no ignition because we have no spark plugs, right? So this delay period here, that the combustion still not happen because ignition not happen, can be divided into 2 overlapping parts. Right? The first one is the physical delay. Right? This is the delay time for the cold fuel droplet to be heated. Right? The time for the fuel to be heated and to be vaporized and then mixed with the air and raise the temperatures of this called the physical delay. Okay, in this first state of combustion, right? And then they have the second delay called the chemical delay. This is where the combustion reaction proceeds, right? But it proceeds very slowly, because no flame happen, no ignition happen, right? But the chemical reaction already happened, but it happened very slow, right? And then it will accelerate itself, right? Until the local inflammation or ignition take place, right? So this chemical reaction like gradually accelerate itself until the flame happen or ignition happen, right? And that the combustion start to happen, right? So when combustion start to happen, it will come in the second state. We call it a premix combustion phase, right? Premix combustion phase, right? Where the fuel, right, that burn very rapidly, right? And the velocity of burning, right, is controlled by the chemical kinetics, right? The chemical kinetic energy, right, control the velocity of the burning, right? And the fuel burn very rapidly. That's why we see the heat go up very fast. Okay, this the partial combustion of the fuel also happen. Right? Not all the fuel that burn in this premix combustion. Right? What you see is just the partial combustion of the fuel because the fuel continue to be injected during this period, right? Right? You still have the fuel injections in this period, right? No stopping of the fuel injections. Yeah. Okay. So in the second step, the fuel start to burn and it burn rapidly, right? Okay, but not all the fuel is burned because you keep injecting the fuel in during this second stage of combustion. Okay. Then the main combustion come after in the third stage that we call mixed control combustion phase, or we call it diffusion of flame. That means flame start to diffuse out from the combustion place, or the point where the combustion happen, flame start to diffuse. That's why we call it diffusion phase, diffusion flame here. Okay, in this state here, right, you can see that the piston start to move down and start to increase the volume of the cylinder. So it happened in the expansion stroke, right? So that means the end of this state, right, is when the piston move away from the top dead center, right? And this end of this state, right, is known by, notice the point where we have a maximum cycle temperature, right? So when the cycle have a maximum temperature that happen along the way that the piston move down, that represent the end of this state here, right? The rate of combustions, how fast that combustion can happen in this state, is mainly determined by how rapidly the fuel vapor are heated and mixed with the air, because we still keep injecting the fuel, right? So how fast that the fuel itself is heated and mixed with the air, right? This will determine the rate of the combustions in this state here. Okay, and this period duration, or the time for this period to finish, the time for this period to finish is affected by, first, how much of the fuel that you inject in this state, the turbulence that happen in the cylinder, and the injection pressure of the fuel here. Okay, so this is the main combustion here, right? You keep injecting the fuel while the piston is moving down. So the main combustion happen during the expansion stroke here, right? And the duration depend on these three parameters here, right? That how fast that you can finish this state of combustion. Okay, and the last state is the late combustion, the late combustion phase, right? We call after burning, late combustion state here, right? It starts from the point of the maximum cycles, right? In this phase here, you can see that the heat release rate gradually drop to zero, right? So it means here, right, it's gradually go down to zero, or start to dry out to zero here. This is the fourth state of combustion here, which we call it the late combustion phase here. Okay, so in overall, this is what you see, right? If you make a plot between the rate of the heat release and the crank angles, right? Remember, this is the plot between the rate of heat release, not the pressures. Okay, so it starts from here, right? Start of injection, you don't see any heat transfer here, right? So this is called the ignition delay period, right? You don't see any heat transfer here, right? Until combustion happen, right? You come into the premix combustion phase here. You see the highest peak of the rate, right? In terms of rate, not amount. Okay, the rate of heat release is highest during the premix combustion phase here, right? Because only partial burning of the fuel happen here, right? And it happened almost immediately, right? When the fuel is injected into the air that already have a high temperatures, right? So ignition and combustion nearly happen at the same time. Okay, so ignition happen here and here. So you don't need, you should not be confused for this word here, right? When if when they said it's the ignition delay period here, there is no ignitions happen here. Only the fuel is injected here, and ignition happen here, and combustion also happen nearly at the same time. Okay, so ignition delay period doesn't mean you ignite, no ignition, what happened, whatever, right? Only the fuel is injected because you don't see any heat transfer here. Okay, and then you see a large rate of heat transfer happen. Okay, yeah, that means ignition happen and then combustion happen, right? And then the rates go down. The rate go down here, right? While you keep continuing injected fuel, right? Because only partial of the fuel is burning in here. And then after that, the rate go up because now more and more of the fuel that injected is now burning, right? More and more fuel are now burning. Okay, so it have a mixing, control, combustion phase here, right? And it lists another maximum here. And after that, you start to reduce the amount of the fuel injections. So the rate of heat release start to reduce. Right? And then you stop inject here. Right? After that, it's going to be the less combustion. That combustion happen to the less of the fuel that is still inside the combustion due to the last injections. Right? You have the late combustion phase here. Okay, so this is where each state of combustion happen according to the rate of heat release. Okay. Now, if we want to make a plot between the pressure and the crank angle, it shows like this. Right? We have the ignition delay period here. Right? That start of injections, not start of ignitions. Right? So the fuel start injection here, and it keep continue injection until the end of the third state here, right? So this is the period of the fuel injection here. Yeah, right. Until at the end of the third state is no more injections, right? But it still have late after burning, right? Or late combustion here because of the fuel that left over. Okay, and then the combustion start right here, right? Because you can see the rise of the pressure again, right? Deviate from the motoring curve. So you know that the combustion start here. So ignition happen here, combustion happen here. And then it go up to the peak pressure near the top dead center. This one is too good to be true, right? It make just close, very close to the top dead center here. And then the pressure start to reduce, right? Because the expansion already happened. The expansion stop already happened. Right? The fuel still keep injecting in this state here, right? And the pressure keep going down, right? Until at this point here, no more injection of the fuel, the pressure keep going down more and more here. Okay, so this is what happened, right? About the pressure in the cylinder for the CI engine combustions. Okay. Okay. NOx can also happen in the CI engine, right? Same as in the SI engine. Right? But the mechanism of NOx that happen in CI engine is like this. Right? It happened when the first peak in the pressure rate diagram is high enough. Right? Not because of the temperature high. It happened because of the first peak in the pressure rate diagram is high enough, and that the knocking sound happened. Okay, this high peak pressure happened because what? Because you have too long ignition delay period. So that means what? The amount of the fuel injected is too large before the combustion happened. Right? That's the result of long ignition delay period. Right? You injecting the fuel too long before the combustion happens. So the amount of the fuel is large. Okay. So by reducing this ignition delay period or injection period here, or by reducing the rate of the fuel injections during the ignition delay period can help preventing the knock to happen. So two ways that you can reduce the knocks is reducing the time for ignition delay period. Right. Remember, ignition delay period is not the same as ignition lag state. Right. That is when the ignition happens. Right. But ignition delay period in the CI engine is when you start to injecting the fuel. Okay. So you reduce the time for this delay period, or by reducing the amount of the fuel that inject during this period. These two can help preventing the knocks to happen. Okay, so this is what happens when there is a knock in the CI engine. Again, you see the pressure pulse that happen, right? This is too high peak pressure. The peak supposed to be somewhere here, but it just go up like this, right? So result in a very strong knocks. You can see it's strong knock because the pulse happen all the way until it's finished. Right? The pressure pulse happen all the way, and this is a slightly knock, right? Because you can have some peak pressure that you want, right? And when the peak pressure reduce, it suddenly you have another peak come out here, right? This is considered to be a slight knocks, right? So it's go like this, and then it die out, right? Gradually die out. You don't see any pulse here. If you see it, just very, very small one, not like the first one that you still noticeable pulse, pressure pulse here, right? And for the normal compression, combustions, you don't see any pressure pulse. Okay, so this diagram, right? From this diagram, you can recognize that knocks can happen or not happen in the CI engine. Okay, so again, the same as in the SI engine, we have to look at the factor that affecting the normal, the combustion in the CI engines, right? And we only look at the ignition delay periods, right? The factor that affects the combustion in the CI engine. We only look at the ignition delay period because this is a very important one, right? Important step in the combustion of the CI engine. The first one is the injection timing. Injection timing, right? At normal engine conditions, right? No matter it's a low to medium diesel engine and a fully warm engines, right? The minimum ignition delay, right, that occur with the start of the injection at about 10 to 15 before top dead center. This is usually the number of the crank angles, right, for the injection to happen. Right? The ignition delay time, right, should be about 10 to 15 degrees of crank angle before the top dead center. Right? However, if we increase the ignition delay time with earlier means before 10 to 15 before top dead center, for example, 20 degrees before top dead centers, or later, that means near the top dead center, for example, 5 degrees before top dead center, right, that we start to inject the fuel. Right? So if we increase the ignition delay time like this, right, for the injection timing, right, this can be occurred. This kind of thing can be occurred because of what? Because of the air temperature and pressure that change significantly close to the top dead center due to compressions. Right? As the piston moves down closer and closer to the top dead center, right? Since inside is only the air, right? So the temperature of the air or the pressure of the air inside, right, can shake significantly when the piston move close to the top dead center because of higher compression that keep going on here, right? So the ignition delay time can be increased or by earlier or later because of this, right? And if it happened earlier, right, the initial temperature and the initial pressure of the air at that time are lower, right? So it takes time before the combustion happens because of the temperature of the air and the pressure of the air is low, right? So the ignition delay period increase. This will happen if the injection start earlier. If the injection start later, right, at that time the temperature and the pressure of the air are slightly higher, but then it decrease. Because it's close to the top dead center, and after that it behind the top dead center, right? It's away from the top dead center. So the temperature of the air and the pressure of the air are initially slightly high, and then later on decrease, right? As the ignition delay proceed, that means as you keep injecting the fuel, right? So it will not help the combustion to happen because of the temperature of the air and the pressure of the air that's supposed to be keep going up, it go down. Okay, so injection that start earlier and injection that start later, right? Both are not do any benefit for the combustion to happen early. Okay, so the most favorable conditions it lie in between 10 to 15 before the top dead center. So this is the most proper timing, right, for you to inject the fuel into the engine. 10 degrees before top dead center to 15 degrees before top dead center. Okay. So this is the first factor about the injection timing. The second factor is about the amount of the fuel injected, right, or injection quantity, which depend on the load, right? So they say injection quantity or load, right? So for the CI engine, right, we do not control the amount of the air, right? So the load to the engine can be varied by changing the amount of the fuel injection, right? Okay. If we increasing the load, that means our BMEP, right, the brake mean effective pressure increase, right? It means we increase the residual gas and also increase the wall temperature, right? So by increasing the residual gas and increasing the wall temperature, this will result in a higher air fuel mixture temperature during injections, right? So it will help decreasing the ignition delay, right? So increasing the load, that means BMEP increase. You can see that our ignition delay increase. So that means combustion happen faster. Okay, combustion happen faster here. Okay. But there is one condition that against this, right? That condition is when you start the engine, right? Under the engine starting conditions, right? Ignition delay do not decrease but increase because of the mixing temperature drop, right? During the starting condition, not continuous running, right? After your engine continue running, this condition do not happen, right? Only at the starting condition, because during the starting condition, your ignition delay increase because of the mixing temperature drop. Why the mixing temperature drop? Because of there is a evaporation of the fuel, right? And also heating the increased amount of the fuel. Right? More fuel coming in, and you need fuel to evaporate. Right? So the temperature of the mixing drop because of evaporations. Yeah. Okay. So that is the second parameter, the injecting amount or injection quantity of the fuel. The third variable is on the droplet size of the fuel, the injection velocity, and the rate of injections. Right? These three quantity, right, no matter it's a droplet size, injection velocity, and the rate of injections, are determined by injection pressure, the size of the injection nozzle hole, the nozzle types, right? We have pintle type and multi-hole type, and also the geometry of the nozzle. Right? So they are affected by these parameters. At normal operating conditions, right, if you increase the injection pressure, right, the effects on the ignition delay to decrease is very small. Right? Under normal operating condition, right, you increase your fuel injection pressure, right, and you hope that you can decrease the ignition delay. Of course, yes, you can decrease, but only small decrease happen for the ignition delay. Right? Okay. And the injection nozzle diameter, which we mentioned in here, right? The size of the nozzle hole here, right? The injector nozzle diameter, right? Even though it affects the droplet size, right? But it had no significant effects on the ignition delay, right? So in overall, what that they said is that the third parameter that we talk about, the droplet size, right, and also the injection velocity and the rate, right? Of this, even though that it depends on the injection pressure, the injector nozzle hole size, nozzle type, nozzle type, and the geometry, right? But if you look at the injection pressure, it does small effects on decreasing in the ignition delay, right? And also, if you look at the size of the hole for the injector nozzles, right, even though it has the effect on the droplet size, right? The droplet size determines how fast that the fuel can evaporate, and that means that related to the time for the ignition delay and the time for the combustion to start. Right? Even though that it affects this droplet size, but it had no significant effects on the ignition delay. Right? So these two in overall, the injection pressure and the injector nozzle hole size. Right? In conclusion, it has little effects on the decrease in ignition delay here. Okay. The fourth parameters is on the intake air temperature and pressures. Of course, this is the common type, right? If we can increase in either one of these, right, we can definitely reduce the ignition delay, right? But if you look at this, right, this make a part between the ignition delay time and the 1 over the temperatures, right? You can see that if we increase the pressure, the ignition delay time reduce, combustion happen faster. And if we increase the temperature, right, go along this line here, increasing the temperature, the ignition delay also reduce. Right? But if you go above 1000 Kelvin, right, if your combustion is above 1000 Kelvin here, these two, right, no matter is the air temperature and the pressure, now no longer play any significant effects to the ignition delay. Right? So for temperature above 100 Kelvin, right, the effect of intake air condition is no longer significant. Okay. But under it have. Okay. The fifth parameter is on the engine speed. Right? By increasing the engine speed at the constant load, we increase the air motions and also the turbulence. Right? And the result is the temperature and the pressure increase. Right? But again, this only slightly reduce the ignition delay time, as we already mentioned, right? Because the ignition delay time, we're talking in terms of milliseconds, but the engine speed is talking in terms of seconds. Okay. But in terms of crank angle degree, right? Not in terms of the speed, but if we talk in terms of the crank angle degree, right? The ignition delay increase almost linearly as the engine speed. Right? In terms of time, it makes no difference. But in terms of crank angle degree, right, the ignition delay increase almost linearly as the engine speed increase. Because of what? Because of the amount of the injected fuel increase. Okay, the amount of injected fuel increase here. And moreover, right, a change in the engine speed will result in the change of the rate of temperature and the pressure rise, right? So the change in the engine speed is not directly affects, but indirectly affect because it's related to the crank angle degree, right? Where the injection delay increase almost linearly as the engine speed increase because of the amount of injected fuel increase, and the change of the engine speed result in the change in the rate of the temperature and pressure rise. Right. So these two affects the ignition delay period. Okay. Number 6 is on the combustion chamber design. Right. How you design the combustion chamber. Right. Because the fuel is injected in the combustion chamber as a spray, and this spray will impinge on the combustion chamber wall, right? And the impingement of this spray will affect the fuel evaporation and the mixing processes, right? So decrease the ignition delay, right? If you have a low pressure and low temperatures, right? So for the low pressure and low temperature, spray impingement, right, have the effects on decreasing of the ignition delay. But for high pressure and high temperature, right, it have no significant effect because the mixture already at high pressure and at high temperature already, right? So it can be ignited easily, right, by itself due to its high pressure and high temperature. So the spray impingement on the combustion chamber wall will have so little effects on that. Right? So if you run the engine at the low temperature and low pressure condition, right, you need the spray impingement on the combustion chamber wall in order to decrease the ignition delay. Okay. Apart from this, also if you reduce the stoke volume, right, you go for a smaller size of the engine. By using that, you can increase the surface area to the volume ratio, right? Surface area to the volume ratio increase by reducing the volume of the engine. And that means you increase the engine cooling, right? So by increase the engine cooling, you are going to increase the ignition delay, right? So if you design for smaller engine, you have to beware of increasing the ignition delay. Right? So this is all about the combustion chamber design. Right? So if you have higher temperature or higher temperature already due to higher compression ratio, right? You need little concern on the combustion chamber design because you already have shorter ignition delay due to that high pressure and high temperature. But if you go for lower compression ratio, right, that means you have lower pressure, you will have lower temperature. Now the ignition delay depends on the way you design the combustion chamber, because the impingement on the combustion chamber wall, right, can affect the fuel evaporation and the mixing process. Right? And for the engine size, like if you go for smaller size of the engine, okay, it result in the increasing of the surface to volume ratio, right? And by this, it increase the engine cooling, which result in the increase in the ignition delay. So that means when you design for a small engine, you have to concern about the ignition delay. Okay, that might happen. A longer one might happen. Number 7, on the oxygen concentrations. Right. Number 7, on the oxygen concentration. The residual gas that left over in the combustion chamber can reduce the amount of the oxygen concentration. Right? And this will increase the ignition delay. Right? So you have to design such that the exhaust can bring all the oxygen that happen go out, because the diesel engine go for the lean mixture. So you expect to have the exhaust, the oxygen left over in the exhaust gas, right? And it have to be brought out from the combustion chamber. Otherwise, it's gonna increase the ignition delay. Number 8 is on the swirl rate. How much that you can swirl the air. Okay. At normal operating engine speed, right, the effects on the swirl rate change, right, that have on the ignition delay is small. So at normal operating engine conditions, right, this swirl rate pay on a very small low or not significant on the ignition delay. Right? But under engine starting conditions, right, under engine starting condition. So when you start the engine, this swirl rate, right, is much more important, because you will get the higher rate of evaporation and also higher rate of mixing from higher swirl rate that you introduce into the combustion chambers. Right? Only under starting conditions, right, that this affects the ignition delay period or the injection period. Okay. Number 9, right, the last one, right, the same as the gasoline fuel. Right? In gasoline, we have octane number. Right? In diesel, we have C10 number. Right? The C10 number of the diesel fuel refer to the ease or easily with which the fuel can be ignited. Right? Can be ignited. The best diesel fuel is that with ignition can be happen easily and burn steadily and rapidly. This is the best diesel fuel. Right? The best diesel fuel have to be easily to ignite. And when it burns, it will give us a steadily and rapidly burning. Okay. Right? So the performance of those mentions, right, easy to ignite and burn steadily and rapidly, is related by means of a scale called the C10 rating. The C10 rating, right? The C10 number assigned to a diesel fuel is the measure of its ignition quality compared to those of a standard fuel or reference fuel, right, in which the reference fuel used for setting up the cetane number is a normal cetane. We call it a normal cetane or N-hexadecane here, C16H34 here. Okay. This isocetane, right? This isocetane, which is called heptamethyl-nonane here, HMN, has a cetane number of 15, right? Not 0. Cetane number, no 0 cetane number. Okay, so that means what? Because of what? All the fuel can be ignited, right? But it just depends on how fast or how slow that it can be ignited. But it no fuel that cannot be ignited, right? So cetane number does not start up with 0. It starts with 15. Okay, and cetane with it N-hexadecane here, right, has a value of 100. Okay, so we have two reference diesel fuel. One is the isocetane and another is the cetane, right? Compared with the SI engine, we have isooctane, right? And another one, right? But this, they also have two reference, right? Okay, so for low cetane fuel, right, or the cetane number of the fuel is low, the ignition delay is long, right? So that means what? Most of the fuel is injected before auto ignition occurs and burn rapidly, right? So for ignition delay, long ignition delay here, amount of the fuel before auto ignition happen and burning happen, right? The amount of fuel is large because of the long ignition delay. So under this long ignition delay, right, you might hear an audible knocking sound that referred to as the diesel knocks happen. Okay. So this happens for a low cetane fuel because you have a long ignition delay here. So knocking might happen. For high cetane fuels, right, the ignition delay is short. So that means what? Very small amount of the fuel is injected before auto ignition occurs. Okay, so knocks can hardly happen, right, when burning happens. The heat release rate is controlled by amount of the rate of fuel injection and the fuel air mixing, right, in order to have a smooth engine operations, right? So the amount of heat release, right, does not depend on the octane number or the cetane number of the fuels. So this is something that you have to understand. Okay, cetane number does not represent that if you go for higher cetane number, you have higher amount of the heat release. No, because the heat release rate is controlled by the rate of the amount of the fuel that you injected and how good that the fuel and air mix together. Okay, and you have to control the amount of heat release in order to have a smoother engine operation. The cetane number is just to prevent the engine, right, to go knocking. Okay, so in conclusion, higher cetane, you have a better ignition quality. That means you have a shorter ignition delay, so the combustion can happen faster. So since we talk about the cetane and the octane number, right, both are inversely correlated, right? What do we mean inversely correlated? It means what? The gasoline fuel is a poor diesel fuel, and the diesel fuel is a poor gasoline, right? So that means what? Low cetane number will correspond to the high octane number. So if you want to use the diesel fuel for your gasoline engine, you have to go for a low cetane number, which I think is not available in the market. Okay, so that is for our lecture today. I think yes. Okay. So any questions? Any questions for these lectures? The combustion in the CI engine. For the CI engine, the combustion problem is not that complicated when compared with the SI engines, because ignition and combustion happen together almost immediately. Ignition happen, combustion happen. Okay. But for the SI engine, ignition happen and then you have to wait until the combustion happen. Okay. Any questions? มีคำถามอะไรไหม มีไหม
อาจารย์ครับ
อาจารย์คะอยากถามเกี่ยวกับการบ้านครั้งที่แล้วนิดนึงอะค่ะ
ไม่ถามเลคเชอร์ ถามการบ้านนะ ว่าไงเหรอทำไมเหรอ
อยากรู้ว่าข้อแรกที่ถามว่า suction pressure อะค่ะไอ้คำว่า suction pressure เนี่ยมันคือP out ลบ P in หรือว่ามันคือ P out เลยอะค่ะ
suction pressure เนี่ยหมายถึง pressure ที่ตรงคอคอดไง
ตรงคอคอด
ใช่ถูกไหมใช่ป่ะ
ค่ะ
นะเพราะฉะนั้นเนี่ยมันขึ้นอยู่กับ pressure ที่ตกค่อมตรงนี้ถูกไหมเพราะฉะนั้น pressure ต้นทางคือ pressure ของอากาศที่วิ่งเข้ามาส่วนใหญ่ก็คือเป็น atmospheric pressure เพราะว่าไอ้ตรง venturi ไอ้ตรงท่อที่นำอากาศเข้ามามันสั้นมาก pressure loss เราไม่คิดถูกไหมเพราะฉะนั้นอากาศก็มาจากบรรยากาศถูกไหมใช่ป่ะแล้วพอมันเข้ามาถึงตรง suction เนี่ยความดันอากาศมันลดลงมาเหลือเท่ากับ suction ถูกป่ะเพราะฉะนั้นก็จะเกิด pressure drop ไง P in ลบ P out ตรงนั้นนะเข้าใจยัง
แสดงว่า suction คือ pressure drop ใช่ไหมคะ
ใช่ก็ suction คือ pressure ที่เกิดขึ้นที่ตรงนั้นยังไม่ใช่เป็น pressure drop เพราะมันมีศักดิ์เป็น suction pressure ไงก็คือ pressure ตรงคอคอด
โอเคค่ะ
pressure ตรงคอคอดถูกไหมเพราะฉะนั้นคุณมี pressure 2 ตัวแล้วไงถูกป่ะ pressure ก่อนเข้ากับ pressure ตรงคอคอดไงถูกไหมเพราะฉะนั้น in and out ก็คือมัน drop เท่าไหร่ถูกไหมคุณไปคิดถึงตั้งแต่มันวิ่งเลยออกมา suction เลยคุณก็หาไม่เจอหรอก ใช่ไหมเพราะพอเลยออกมาแล้วมันไม่ได้ไอปริมาณของอากาศที่ไหลผ่านเนี่ยนะพอมันไหลผ่านตรงนั้นที่เหลือปริมาณอากาศเป็นยังไงล่ะเท่าเดิมถูกไหม common sense คุณจะได้เข้าใจไงถูกไหมใช่ป่ะอากาศถ้ามันยังวิ่งมาเรื่อยๆเนี่ยปริมาณอากาศมันไม่เปลี่ยนหรอกแต่ว่ามันไปเจอช่องแคบปุ๊บเนี่ยนะอัตราการไหลมันเปลี่ยนถูกไหมพอมันเลยช่องแคบไปปุ๊บอัตราการไหลมันเปลี่ยนไหมมันก็ไม่เปลี่ยนแล้วไงถูกป่ะใช่ไหมฮัลโหลฮัลโหล
ค่ะอาจารย์
จะได้เข้าใจไงจะได้ไม่ confuse นะเราต้องเห็นภาพอย่างนี้นะครับนะเราจะคิด pressure drop ตรงที่อัตราการไหลมันเปลี่ยนนะครับเราถึงใช้ความดันลดมาวัดอัตราการไหลได้นะครับโอเคมีใครถามอีกไหม any questions มีใครถามอะไรอีกไหมครับมีไหมถ้าไม่มีนะครับก็เตรียมตัวสอบนะว่าไงครับ
ไอข้อเดิมเลยครับผมคือเหมือนกับว่าในโจทย์มันให้ volumetric efficiency มาครับแล้วทีนี้นี่ถ้าสมมุติตามสูตรไอ volumetric efficiency มันคือสามารถหา mass flow rate ของ air ได้ใช่ไหมครับก็
ต้องเอา density ไปคูณไง
ครับไอ mass flow rate ตัวนี้มันคือ actual หรือว่ามันเป็นของ theoretical ครับ
ถ้าคุณไม่มี CD เข้าไปคูณใช่ไหมมันอยู่ที่ว่าอย่างนี้ต้องมองอย่างนี้ว่าคุณคิดจากการไหลผ่านออริฟิศหรือเปล่าหรือคุณคิดจาก volumetric efficiency ถ้าคุณคิดจาก volumetric efficiency มันจะมี actual volume หารด้วยอะไรโดยนิยามของมันถูกไหมใช่ป่ะเพราะฉะนั้นถ้าคุณคิดจาก volumetric efficiency คุณจะได้ either actual volume หรือไอ้เจ้า volume ของ displacement ถูกไหมมันไม่ใช่เกี่ยวกับ CD แล้วถูกไหมแต่ถ้าคุณคิดจาก Orifit อันนั้นน่ะ CD เข้ามาเกี่ยวข้องถูกป่ะถูกไหมนะเพราะ volumetric คือ actual volume หารด้วย volume ที่เป็น displaced โดยนิยามมันถูกป่ะนะโอเค
ขอบคุณครับ
มีคำถามอะไรไหมครับมีไหมถ้าไม่มีก็จะได้ปิดบรรยายเท่านี้นะครับนะ
สอบกี่ข้อคะอาจารย์
ผมบอกไปแล้วนี่มี5ข้อไม่ใช่เหรอใช่ไหม5ข้อ3ชั่วโมงนะครับ5ข้อ3ชั่วโมงนะ
มันยากไหมครับยากกว่ากันบ้านเยอะ
พอๆกันแหละมันไม่ได้แบบนั่นหรอกนะเพียงแต่ว่ามันก็มีอะไรที่อะไรเพราะการบ้านมันคุมได้ไม่หมดอยู่แล้วนี่ถูกไหมการบ้านของคุณทำแค่กี่ข้อ3ข้อใช่ไหมเพราะผมจะให้เป็นคุณเป็น100ข้อมันคงไม่ได้หรอกถูกไหมนะเพราะคุณ
เยอะเกินครับ100 ข้อ
นะแต่คุณสังเกตเห็นป่ะไอ้หนังสือเทอร์โมอะไรที่คุณเรียนทั้งหลายแหล่หรือสแตติกเนี่ยเห็นไหมแบบฝึกหัดเขามีเท่าไหร่
เกิน100ครับ
เพราะว่าเขารู้ว่าคุณจะเข้าใจเนื้อหาได้จากการทำแบบฝึกหัดเพราะฉะนั้นถ้าคุณทำยิ่งเยอะเนี่ยเท่ากับว่าคุณจะต้องไปพลิกเนื้อหาเพื่อมาตอบมากขึ้นแล้วการที่คุณไปพลิกเนื้อหามาตอบมากขึ้นก็ทำให้คุณเข้าใจเนื้อหาได้มากขึ้นถูกไหมเพราะฉะนั้นความเข้าใจมันเกิดจากการที่เราได้ใช้เนื้อหาเอามาแก้ปัญหาก็คือการที่คุณทำโจทย์มากขึ้นเนี่ยใช่ไหมเพราะฉะนั้นที่เหลือเนี่ยผมให้ไปคือส่วนหนึ่งที่เหลือคุณก็ต้องไปทำมากขึ้นซึ่งก็มาจากพวก reference book ที่ให้ไปทั้งหมดคุณก็ไปทำโจทย์มากขึ้นซึ่งอันนี้ไม่ผิดเลยนะเพราะว่าอะไรเพราะว่าเราเรียนอยู่บนพื้นฐานของอะไรถ้าคุณไปดูไอ้หลักสูตรใช่ไหมชื่อวิชาเสร็จแล้วมันจะตามด้วยตัวเลขอะไร3-0-6ถูกป่ะเข้าใจว่าไอ้3-0-6
ครับ
นะมันไม่ใช่แค่3ชั่วโมงนะวิชาหนึ่งจริงๆคุณต้องใช้9ชั่วโมงนะถูกป่ะนี่คือที่เขากำหนดคือมินิมัมเลยนะ9ชั่วโมงว่าอันนี้แต่ไอ้บ้านเราไอ้เลข6มันชอบลืมไงเพราะฉะนั้นพวกคุณต้องลงเทอมหนึ่งกี่วิชา5-6 วิชาคุณเนี่ยทำงานหนักกว่าคนทำงานออฟฟิศอีกหรือว่าวิชาหนึ่ง9ชั่วโมงเอา6วิชาไปคุณใช้เวลาเท่าไหร่54ชั่วโมงนะคนทำงานออฟฟิศก็ทำแค่40ชั่วโมงเองนะอาทิตย์หนึ่งไอเนี้ยผมยังขำไม่หายอยู่เนี่ยเขียนกันไปได้เนี่ยเขียนแล้วไม่เคารพในสิ่งที่ตัวเองเขียนให้เด็กเรานี่ทำงาน54ชั่วโมงว่าไงครับมีคำถามไหมถ้าไม่มีก็ปิดนะแล้วก็อาทิตย์หน้าก็สอบนะครับนะโอเคถ้ามีคำถามอื่นก็ถามในกลุ่มไลน์ได้นะครับโอเคนะครับวันนี้ก็พอเท่านี้นะครับ
อาจารย์ครับขอเน้นครับ
ว่าไงครับ
ออกทั้งคำนวณและบรรยายผสมกันใช่ไหมครับ
ก็มีทั้ง2อย่างมีทั้ง2อย่างแน่นอนอยู่แล้วอันนึงก็ความเข้าใจอีกอันหนึ่งก็คือเป็นความเข้าใจในเชิงของการเห็นภาพแล้วคุณบรรยายออกมาได้นะกับความเข้าใจในเชิงว่าเข้าใจแล้วสามารถนำมาคำนวณเพื่อให้เกิดสิ่งที่มันเป็นจริงได้เพราะการคำนวณมันทำให้เกิดสิ่งที่เป็นจริงได้ไม่มีการคำนวณคุณจะทำให้สิ่งนั้นเกิดขึ้นมาไม่ได้นะใช่ไหมถ้าคุณไม่คำนวณในสิ่งนั้นเกิดขึ้นมาไม่ได้หรอกนะเกิดขึ้นมาได้คุณก็ไม่รู้มันจะใช้งานได้หรือเปล่านะแต่ถ้าคำนวณขึ้นมาปุ๊บคุณจะรู้แล้วว่าคุณจะทำสิ่งนั้นขึ้นมาอย่างไรมันก็เลยมี2อย่างไงนะครับทั้งคำนวณกับบรรยายมีแน่นอนนะ
ขอบคุณครับ
ครับโอเคครับ
อาจารย์คะ
ครับ
จะรบกวนอาจารย์ช่วยโพสเฉลยกันบ้านได้ไหมคะ
เฉลยการบ้านที่จริงเนี่ยคือคำตอบคุณตรงไหมล่ะถ้าไม่ตรงเดี๋ยวเอามาถามกันดีกว่านะครับจะได้อธิบายได้นะถ้าคำตอบไม่ตรงนะครับเพราะอะไรรู้ไหมเพราะเฉลยคือคุณต้องเข้าใจนิดนึงคือไม่งั้นเนี่ยผมก็ต้องถ้าผมโพสเฉลยไปเนี่ยไอ้เฉลยนี่มันก็จะถูกแจกจ่ายไปแล้วมันสุดท้าย รุ่นต่อมาก็เฮ้ยไม่ต้องคิดมากหรอกใช่ไหมนะมันจะเป็นอย่างนี้ไงถึงไม่อยากที่จะโพสต์เฉลยไปเอาแต่คำตอบนะแล้วทุกคนก็ไปนั่งทำแต่ถ้าติดเมื่อไหร่ก็มาถามแล้วเดี๋ยวก็จะอธิบายให้ฟังว่าจะต้องตรงไหนยังไงนะครับนะเพราะถ้าโพสต์ออกไปแล้วรับรองมันไปถึงมือรุ่นต่อไปหมดนะครับนะก็เลยไม่เคยอยากโพสต์เท่าไหร่แต่จริงๆแล้วเนี่ยถ้าคุณไปเซิร์ชในเน็ตก็ไม่แน่นะครับนะก็อาจจะมีเฉลยพวกนี้โผล่มาเคยลองยังเคยลองไหมฮัลโหลอ้าวเคยลอง
ลอง
ป่ะ
เราไม่เจอค่ะอาจารย์
สมัยก่อนคุณรู้ว่าที่เขาต้องยึดมือถือนะก็เพราะเหตุผลนี้รู้ไหมนะแล้วมันมาจากเด็กอินเตอร์ด้วยทำให้อาจารย์ได้เรียนรู้ไงเพราะว่าสมัยก่อนเขาไม่ยึดมือถือก็ยังอยู่บนโต๊ะสอบของเด็กแล้วปรากฏว่าเด็กไปพิมพ์โจทย์ใน Google แล้วมันมีคำตอบขึ้นมา อาจารย์แล้วหลังถึงมารู้ทีหลังเด็กอีกนะเนี่ย เขาก็เลยต้องยึดมือถือออกมาหมดเลยไอ้พวกรุ่นแรกๆนี่โชคดีมากเลยเพราะเขาไม่รู้เรื่องไม่รู้ให้มันมีคำตอบอยู่ใน Google ด้วยเว้ย โอเคครับงั้นวันนี้พอเท่านี้นะครับโอเคครับสวัสดีครับ
ขอบคุณครับ
สวัสดีครับ